you, Marcellino. Thank you for the kind words. And also, to be honest, my first choice would have been George Clooney, but when I shared George Clooney with the family, with my kids and my wife, they said I'm not handsome enough. So I settled on Tom Hanks when you asked me who the character should be. I notice we're a little bit German-centric this morning, so you'll have to bear with another German origin speaker. But as Marcellino said, I've spent 10 years here in San Diego, so this feels like my second home or third home. My second home is actually Milan, Italy. And what I would like to do during my speech today is not talk a lot about products and what we develop, but how we develop. And what we are trying to do at ST, we are trying to innovate also in that space. So we're all used to innovating at product level, but I believe this project that I'll be sharing with you is an interesting way of how we actually develop these products in a very, I would say, networked and open innovation manner. And the topic of the speech is the world's first Lab-in-Fab, which is quite a unique organizational structure that we have set up in Singapore with the aim of accelerating MEMS technologies from development to scalability. And I'll start off with a few words on the idea, what is the concept behind this Lab-in-Fab. We have chosen to focus Lab-in-Fab on Piezo MEMS, so a bit of explanation as to why we have selected Piezo MEMS. Then I'll continue with an overview on the R&D capabilities and really the idea behind scalability of this line, and then I'll draw some conclusions. So MEMS R&D and scalability, at ST I think we have a good track record of doing that. We have shipped more than 25 billion MEMS devices into the market in the past 20 years. And we keep adding more than 1 billion per year. So we know what it means to scale. We have been doing this for the past, as I said, almost 20 years, mostly in Agrate, in our fab outside of Milan, Italy, where we have an R&D team that is integrated into the high-volume production MEMS line. And that has, I would say, has been a good way of doing R&D when you deal with products that are going to ramp up very rapidly. Many of our MEMS products during the past 10, 15 years were driven by smartphone adoption. And as you know, in that case, you really need to go from delivering first samples to very high volume production in a very short period of time. So when you have an R&D line that is really part of the manufacturing line, it's perfect for that. When the world is becoming a little bit more, I would say, not so much driven by a few big accounts and by a few killer applications, and Stefan mentioned that also earlier, but it's becoming more diversified with many small customers and a lot of applications that you know yet exactly how this is going to play out. You need to have the capability to take on projects with a much more longer term view. And that's where we said we will try something different, and I'll explain to you what we have implemented. Before doing that, just a few words on how we see the MEMS environment evolving. To simplify a bit our view, we have defined these 3 eras that we see in our MEMS history. The first one, what we call the offline era, where MEMS devices were a different way of doing a man-machine interface. The Nintendo Wii with an accelerometer, then of course the adoption of MEMS in the smartphone were examples. The MEMS component had to perform a very specific function. Those devices were offline, so the internet was not yet there. Then we moved into the online era, where more and more those MEMS components were meant to collect data, and those data needed to be processed. Sensor fusion became a concept, and then of course these data needed to be uploaded to the cloud because they were in the enabler of services, of applications like location services, etc., etc. The next phase that we are now entering is what we call the Onlife era, where this distinction between online and offline is becoming irrelevant because most or many of the devices that we carry with us are connected all the time. When you think about wearables, when you think about smartwatches that monitor more and more body functions, not also during the day, but also during the night, during your sleep, you'll have these devices always connected. And what becomes more and more important then is to have, as a MEMS component, already a built-in ability to kind of distinguish between data that are relevant and data that are not relevant. So local processing becomes an issue. AI, machine learning, etc., integrated into the companion ASIC of the MEMS device so that you can optimize the battery lifetime of those devices and you don't clog your bandwidth with all the data to be uploaded that you can process locally. So as we looked at that future with MEMS opportunities, we concluded that really thin-film piezo is a very promising technology platform. A very promising technology platform because it allows you to design multiple devices that will all benefit from this trend. Going from MEMS speakers in Piezo MEMS technology to PMUT devices to MEMS mirrors. Another example is a piezo actuator in autofocus devices, replacing a voice coil motor in many applications. So we decided a few years back that we will focus quite a bit of our technology R&D effort on Piezo MEMS. And if we look at today the commercial success of Piezo MEMS, you'll see here on the right-hand side a chart from Yole. I think they published that in 2019, where they already projected a very explosive adoption of Piezo MEMS components into the market. Many of these devices have been launched. Honestly, the commercial success today is still not there compared to our inertial MEMS business and environmental sensors, etc. But there are a few things that are quite encouraging that have happened that make us believe that we are really at the beginning now of this trajectory taking off. And one way of looking at the future is then to look at the past and to say, what can we learn from the past? And we just took a motion MEMS device, an accelerometer, and we said, what was the improvement that the MEMS industry has achieved over 10 years, right? So a device in 2009 and more or less a similar device 10 years later. And you can see here that the power consumption of that device today is only 1/10 of what it used to be 10 years before. The full scale range has doubled. The chip size has gone from 25 square millimeters down to 7.5. And together with that, the industry has achieved an incredible cost reduction. So if that device, say, would cost you $1 to produce 10 years ago, today you would be able to produce it for 25 cents. So if now you apply all these learnings to Piezo MEMS that is just at the beginning, I believe you can imagine how powerful some of these piezo devices can become in the next 5 to 10 years. However, then very often what happens is that developing a first MEMS and producing hundreds of samples, having a proof of concept is not that, I'm not saying it's not that difficult, I would say it's not that expensive compared to other chip technologies. So you can do that if you're a MEMS fabless company by working with universities, with research institutes. They can help you make few wafers and take you through that first learning. Then usually when you get funding from VCs and you have a path to market, you might decide to work with a low volume MEMS partner that can help you make it to the next 2 to 3 years of your journey. And then if you're successful at a certain point, that partner might not have the fab capacity that you need, and then you need to look for a high-volume MEMS fab as a partner. So you can imagine that along this journey, as you're dealing with two process transfers, a lot of money is being wasted, and also a lot of time to volume is being wasted. And we have seen that many times at ST because we have a history of partnering with MEMS fabless companies. We've been doing that for quite a while. And we noticed that this is not the optimal way of working. So what we asked ourselves is, could we do something where we have everything under one roof? And that is really the idea behind Lab-in-Fab, to have a facility in Singapore that we have announced. I think it was in early 2020, so in the midst of the pandemic. And today we can say this is now up and running, it's open for business. And we have set that up together with the Institute of Microelectronics, a local partner in Singapore, and also ULVAC is a founding member of that initiative, letting us use some of their most advanced piezo deposition and etching tools. The picture is actually quite interesting because this fab is the first chip fab ever built in Singapore 60 years ago, not even by SGS. SGS was not existing at that time. It was STMicroelectronics was not existing at that time. It was SGS. And it is a building that we have partially now reconverted to a MEMS clean room and facilitated with MEMS tools, and created that MEMS R&D line that is the beginning of that Lab-in-Fab idea. We're doing that jointly together with the IME. We have chosen to work with a research partner because we believe that working with a research partner, we have that long-term view that a commercial MEMS company cannot always afford to do. So when there are very advanced ideas that maybe ST as a company would not yet take on, we let IME take the lead. But again, everything under the same roof so that these ideas, as they then mature and become a product or become close to a product, they can be easily handed over using the same tool set, even having the same people that are working on that project. Also, IME has been working on Piezo MEMS quite a bit. They have worked on aluminum nitride since 2010, and they are a great partner for us along that journey. So what are we doing there? In Singapore, we have focused on two technology platforms, one being PZT, mostly addressing actuators, and the second one, aluminum nitride, but more going forward, scandium-doped aluminum nitride, more for the sensing and for the transducer applications. So as I said, it's a dedicated 8-inch R&D line. We have today more than 30 tools already installed, and there are another 25 coming and will be ready by mid-23. Clean room, just to give you an idea, of 1,300 square meters. And a significant investment also in terms of engineering resources that are allocated to this activity partially by ST and partially by IME. You see some of the symbols of products that we have currently in the pipeline. And I'll go quick on the technology. I don't want to go too deep on the technical specifics, but as I said, two technology platforms. The one on the left is what we call our PETRA, our PZT technology, where we have been producing 8-inch wafers on sol gel technology in our fab in Agrate now for almost 5 years, where we have been able to get improvements on sol gel on the E31 by applying some doping technique. And sol gel is giving us a great, I would say, performance, giving us great reliability, has some intrinsic limitations in terms of scalability. This is why we are now transitioning over to PVD. We have the tool and the process technology qualified, and we're going to ramp up the first product in early next year. And in parallel with that, we are looking at the multi-layer technology that will enable new product design features by putting several piezo stacks on top of each other. On the right-hand side, scandium-doped aluminum nitride, where we were not, I would say, while on the PZT side, we were clearly the pioneers. Aluminum-doped scandium nitride was more driven by the RF MEMS industry, as many of you probably know, so we came in a little bit late there. Have today 15% doping level qualified, getting close to releasing also 20%, and have a roadmap to go to 30%. And then also with some other deposition technologies, we believe we can go above 30%. And also there, the ultimate goal is to have multi-layer capability as well. Ultimately, of course, all this technology effort needs to translate into the benefit to the customer in the application. And clearly on many of the devices that I've mentioned earlier, low power, small footprint for miniaturization, the ability to drive those devices with a lower voltage, all these things are very important. In terms of accuracy and reliability, Piezo has some additional nice features that you can apply, for example, for MEMS mirrors, where you have an integrated position sensor that is already built into the technology that allows you to monitor the position of your mirror and have a closed-loop system. Companion ASICs are very important. In many of these applications, we are also designing the ASIC that goes together with the MEMS device. And then, of course, a lot of learning from other MEMS components in terms of qualifying and metrology tools, etc. A few pictures here to give you an idea of the state-of-the-art MEMS tools that we have up and running today. And as I said, many more to come. Also here, I won't go into the detail, but maybe just to show you with this chart that there is always a trade-off between you want to have one only technology platform, but at the same time you want to be able to customize that technology platform somehow, because this is unfortunately what is still needed in MEMS. In order to make a good MEMS product, you need to have that capability. As a matter of fact, very often when we are being asked, so is ST now offering MEMS foundry services? The answer is no. We do not consider that MEMS foundry service. We consider that a MEMS code technology development where we have, the fundamental building blocks of these technologies, but then we're willing to adapt them together with our customers and with our users. And this is true for the piezo stack options, the metallization, the passivation options, etc. Just a few examples here, since the first device that we have used in order to debug the tool set and get the line up and running is PMUT. I'm using a PMUT here as an example. You see here some cross sections of the PZT edge, the scandium-doped aluminum nitride edge, and the top and the bottom electrode. Some application examples where we are using the technology in the hundreds of kilohertz, but also in the megahertz range. And here is a good example where you can address, and you're better off addressing some applications with PCT, but then you might have other applications where actually scandium-doped aluminum nitride is the better solution. So having both these piezo capabilities makes us agnostic in that space, and we can offer whatever fits best to the application needs. Some use cases with PMUT in the field of medical imaging, where more and more what is happening is what's called the democratization of ultrasound, where PMUT devices can help take ultrasound, from the doctor, from the specialist office into more portable applications. More and more also using patches where you could wear an ultrasound PMUT on your body for a longer period of time to have continuous monitoring of some body functions. More conventional use in the industrial, where you use it for structural monitoring, etc. And a lot of possible applications in the metaverse for, haptics, presence monitoring, etc. Then, of course, piezo technology, or generally speaking, technology is not what the customers buy. The customer actually buys a product and needs a solution. So on top of the technology effort that we're making, we need to wrap this all into a complete solution. I already mentioned the ASIC design as well. We are offering reference designs on several of these products. Interesting maybe also to know for some of you in the audience, starting in January next year, we will be offering a service of MPW. So if you have a PMUT design need and you want to have first samples built, we can offer you a design environment so you can use your design, put it on an MPW wafer, and with a relatively moderate cost gets first samples from us. And then on the right-hand side, application and system support, characterization, reliability, and also packaging capability. So in terms of engagement model for Lab-in-Fab, of course, we view it as a in-house capability for ST to boost our own Piezo MEMS roadmap. That's clear, but at the same time, we view it as a very attractive proposition to support fabless, MEMS fabless startup companies. I'd like to mention also Silicon Catalyst. You see the Silicon Catalyst logo here on this chart. For those of you who are not familiar with Silicon Catalyst, is an incubator in the Silicon Valley, focused on selecting and scouting and growing promising companies that have an idea around a chip, and we are partnering with them. We are a strategic partner for MEMS. So they help us in selecting these companies, and then we can provide them with the support that they need in order to ramp up first to validate and subsequently ramp up their product. And to wrap it up, for us, there are really three important items related to Lab-in-Fab. The number one is we want to expand our Piezo MEMS leadership in collaboration with the IME. We want to view it as an open innovation site where we are welcoming, as I said, MEMS fabless companies, but we're also welcoming collaboration with tool vendors. We are welcoming collaboration with other research institutes. So this is not meant to be necessarily exclusive with the IME. And lastly, an important point, especially we have experienced that during the past 2 years, it is also a business continuity plan for MEMS at ST, because we will ultimately be able to have two MEMS fabs, one located in Milan, the other one located in Singapore, that can back each other up, and in case unforeseen things happen, and we have seen many unforeseen things happening, unfortunately. So that really takes me to the end of my speech, and I hope I was able to share with you some of the excitement that we have at ST around this project that is really meant to combine innovation with scalability. Innovation ultimately only matters when you have a product that you can scale and that you can sell into high volumes, right? Otherwise, it's an invention, but it is not yet relevant. So that is the part that we are trying to address. And as I said, we are ready to take on projects. So if there is any interest from you, don't hesitate to talk to me while I'm around. Thank you.
Thank you, Anton. We have time for a couple of questions for Anton. Yes.
Thank you. I seem to remember a couple of years back the availability of scandium aluminum nitride sputter targets with high scandium concentration was one of the key issues. Can you comment on that?
At least for our R&D needs, we don't have a problem with that. Now, being honest with you, as I said during my speech, with scandium doped aluminum nitride, at least with the higher doping levels, we are not yet in full production, so I cannot comment on that. But getting targets for what we need for R&D, we don't have a problem with that.
Okay, gotcha, thanks.
You said you're ready to take projects. Are you also open to or interested in taking projects that don't involve the use of piezoelectrics?
The short answer is yes. Then the long answer is as long as they are compatible with the tool set that we are going to install. It will be quite complete at around mid-2023 when we have completed that second phase. It will be a quite complete MEMS tool set that can also address other MEMS devices. We wanted to keep a focus on where we invest most of our R&D money, that is Piezo MEMS. But
Yes.
if we have the capability to support other MEMS devices, yes, we would not say no.
Great, thank you.
You're welcome.
So Anton, thank you for the very interesting talk. My question is, how do you set up the business model? You said it's not a foundry process. In the end, you have to get some money. How do you set up these business models in this Lab-in-Fab approach?
It's a good question. We have been doing similar things for quite a while. Now I can mention a few examples that we have publicly announced. There are companies like U-Sound, and I'm only talking Piezo MEMS now. There are others outside of Piezo MEMS, but in Piezo MEMS we have supported U-Sound with their speaker. We have supported another MEMS fabless company, Polite, in Norway with their autofocus device. We are working with Chirp, now being TDK, and supporting them on their R&D as well as manufacturing. So for customers that are at that phase, I would say we share somehow the burden of funding the R&D, the technology development with them. The sharing then depends on how much we believe in their, in their commercial success. However, what we are now trying to do is we're trying to intercept companies much, much earlier, right? And this is typically where these companies, they don't have deep pockets. They are very often not yet VC funded. This is also where Silicon Catalyst comes in. And that's where we try at the early stage to offer MPWs and support it in such a way so that when they have little money to spend for the first few years just to build some proof of concept, we can support them with that. I believe the big difference is then that if they are successful, they can stay within that same place, right? In the past, they will maybe do that same effort where they don't have money to spend with a research lab, with a university, and then they would have to go and transfer that know-how to someplace else. That's what we are trying to resolve.
Okay, thank you. I would have one more question. So from classical MEMS, there is the law, one product, one process. I think in this Lab-in-Fab approach, you also live from that there is a kind of standardization. You said you want to keep at least a set of tools. Do you see a better chance that you get a kind of standardized process in Piezo MEMS than you have it in classical MEMS?
I mean, you know that this is really the challenge of MEMS. Now, when I talk about the challenge at ST, there are really two technology platforms that we have been able to develop successfully with very high volumes. One is our, what we call Telma technology for inertial, and the other one is our printhead technology platform for very, very specific application. Everything else was is more like relatively small volumes. So with Piezo MEMS, we are kind of designing or developing a piezo stack that we do not want to change. So if we have a PZT stack, with a certain thickness and with a top electrode and the bottom electrode, it would be very difficult to convince us to change that, right? Because that is the heavy R&D effort. And once you have qualified that, you do not want to mess with that. Then what you put on top of that, we are flexible, right? Okay. That's how we are trying to resolve it.
Thank you, Anton. Let's hear it for Anton.